This is the second video about a numerical method for approximating solutions to differential equations called Euler's method. On the screen here I have written what I showed, what I derived in the previous video about Euler's method, the formula for using it, based on using linear approximations to nonlinear curves. Solution curves typically are nonlinear, but Euler's method pieces together linear approximations. This formula that we get here is the formula that you end up using. It's what's called a recursive or sometimes an iterative formula. I'll probably use both words when I describe that. I want to show you in this video how to use Mathematica, at least one way of using Mathematica to implement this. So here I have Mathematica up on the screen. And what I'm about to do is I'm about to type in a bunch of commands at once, separated by semicolons. If you've done any computer programming, it's just essentially one line of code for each part that's separated by a semicolon. I don't have to bother typing them on different lines, though. I can just type them all in one cell, essentially. The first thing I'm going to type is a formula for f of t comma y, the right-hand side of the differential equation that I'm going to use Euler's method to solve for some given initial value. Notice that when I define functions, I need to, in a sense, specify what are variables by putting underscores after the t and the y. And I also need to use the assignment operator colon equals to specify what the formula is. The differential equation that I'm going to use is the same one as the one from the previous video. dy dt equals 2t plus y. So that's what I'm going to type in here, 2t plus y. And unlike the CD-ROM, I don't have to put a multiplication symbol between the 2 and the t. Though you should note that if I had, say, dy dt equals t times y, I don't want to type a t and a y next to each other like that, because Mathematica would think that's one variable, tie, instead of two variables being multiplied, t times y. That's the safe thing to do. You actually can put a space between the t and the y also as another option, though it's always safe to put a multiplication symbol in for that kind of thing. But with numbers, I don't have to. There's my function. Same cell. I'm now going to type in some other things that I'm given, like my initial value of t and my initial value of y. And I'll use the same ones that I used from the previous video. And in fact, I'm going to use subscript notation in Mathematica. It's not that I have to do it, but stylistically it's kind of nice to match it up with what you see in the book. The basic math input palette over here on the right has an option, a button down near the bottom, for putting symbols with subscripts into Mathematica. I'll click on that. Now I'll look up at the top, and you can see that I've got two square boxes that I'm going to be putting my symbols into. What symbols do I want? Well, I want a value for t sub 0. I'll take that to be 0. That's a second command. Now I put another semicolon. I want a value for y sub 0. I'll go back to the palette, click on that to make a subscript notation. And from the previous one, I had y sub 0 being -1. That's what I'll take here. That's my third command. Put another semicolon in. If you recall, I also need to know what delta t is. What is the step size? I'm going to go back to the basic input palette. And I'm going to go ahead and find a delta on there, click it, and type in delta t. Not that you have to. You could do this, delta t, if you liked. But stylistically, I do try to stay consistent with common math notation when I can. So I'm going to go ahead and use the palette like that, and set that equal to 0.5. So we have our point, we've got our function, we've got our step size. Looking back at the screen over here, at this recursive formula, we've got a function, we've got delta t, and we have these numbers at least when k is 0. All that's left to do before I implement this method essentially is to type this formula into it and also type another formula telling the computer how to update t by 0.5 each time. Let's go back to the computer output. How can I do that? Well, here's how. Let me go ahead and type in the formula for updating t. I'm going to go to the palette, click on the same thing I've clicked on before here already, the subscript one, and do this. Type a t sub k, and I'm going to put an underscore after the k. Why am I doing that? Well, really what this is doing is this is emphasizing that t depends on k. In a sense, t is a function of k here, though k can only be an integer. And I arrow over and do a colon equals, because I'm defining this function. T sub k is the previous value of t sub k minus 1, plus delta t. Now you might wonder, why not type t sub k plus 1 equals t sub k plus delta t? Well, I could do that if Mathematica allowed me to, but I tried it and it didn't really like it. So I'm going to leave it like this, which is opposed to the style that's used on the screen here, where I'm finding the k plus first value of y in terms of the kth. Well, when I do it for y up on the computer here, I'm going to find the kth value of y in terms of the k minus first. It's still the same principle. The new value in terms of the preceding value. Let's go back up to the screen. And now type in that recursive formula for Euler's formula. Once again, using the palette, function notation, the subscript after the variable, the colon equals to. Type this in terms of the previous value of y, and you'll note for the previous value of y and the previous value of t, I did not need to put subscripts, or the underline symbol. Plus the slope, or plus the change in y, which is the slope f of t sub k, comma y sub k, k minus 1. That's the slope of the slope field at that point, times delta t. That product gives me the change in y. Don't have to put a semicolon after this next one, but I will typically put semicolons anyway, and so I'll go ahead and put that there. I'm going to go ahead and evaluate this cell all at once. Mathematica has now got all that information recorded in its memory, and we can use it. For example, I could evaluate f of 3 comma 7 if I wanted to. 13, that's the right-hand side evaluated at that point. I could find the value of, say, y sub 2, negative 1.75. That number should look familiar from the previous video. If you go back and look at it, I'll remind you what y sub 3 is also equal to, negative 1.625. If I wanted to change the initial value problem, by the way, it's an easy thing to do. If I wanted to change the initial value of y to be, say, negative 3 instead of negative 1, I just go change that to a negative 3, re-evaluate that cell, and now if I want to find the new value of y sub 3, I can re-evaluate that cell. So this is very flexible. I'll go back up to the top and go back to my original problem now. So you can see, just by doing this, I can find approximations to y sub k. There is one difficulty with this particular approach, in that if the k value gets too big, like even 20, it tends to take Mathematica a while to do it. It's thinking right now. How long will it take? I'm not sure. There we go. That was about maybe 5 seconds or so. Not so bad, perhaps, but if I went up to 30, I'm sure it would take a lot longer, perhaps over a minute or two. And so ultimately, this is not really the most efficient approach for Euler's method, but it does illustrate the idea to you in the simplest way that I can think of for Mathematica. So you can certainly use this to evaluate, to approximate the function at any value of k. Remember, though, that k is not the same as t. Y sub 20, k is 20 there, but that's not what t is when k is 20. You'd have to evaluate t sub 20 to find that. That's 10, meaning, be careful, this number is your approximation for the value of the solution to the initial value problem, not at t equals 20, but rather t equals 10. So you have to be careful to make sure you understand that. What might be one final thing that we would like to do here? It might be nice to plot the polygonal curve that I get from Euler's method. I'm going to use the table command to help me do that. What the table command is going to do is create a list. In this case, it's a list of points. The points themselves, really, in Mathematica are also lists. They're lists that are 2 elements long, like that, inside curly braces. That's a list with 2 elements, but I'm thinking of it as a point. T sub k comma y sub k is going to be my point, and I'm going to use table to essentially calculate this point for many different values of k. Let's say go from 0 to 10. This command is going to create a list of points. Really a list of lists. There it is. You see curly braces inside other curly braces. The big list, the first curly braces there, the end curly braces there. It's really a list with 11 points in it. Those points themselves being sublists of the big list. Using list plot, I can now plot this. I've named this list EM. I used EM for Euler's method. You could name it something else if you like. List plot EM will plot those points. There they are. I can make the points bigger by putting an extra command in the argument of list plot. Plot style point size. I typically like using 0.015, though you can try other numbers there. Well, it looks like that might have been the default for this one. It's not always the default. Let me try something bigger. 0.25. There we go. That's definitely bigger. That's bigger than I typically like using, but you can play around with it, see what you get. You can also change the plot range if you like. Maybe 0 to 5, but only from 0 to 10 for y. We're not seeing all the points now, but that's something you could do if you wanted to. You can also label the axes with axes label, capital A, capital L. I'll let you look that up. And one other thing that I like to do typically with Euler's method, though you don't see the points if I do this, is I like to use this, plot joined arrow true. And it gets rid of the points, it just draws the straight line segments. If I'd like both, let's call this plot 1. if I want both the line segments and the dots, I can quickly do that through copy and paste. Let me get rid of the plot join true here so that I have dots. Let me call this plot 2. And now I can use show to combine plot 1 and plot 2. So there are the dots along with the straight line segments. That's the gist of a basic way you can use Euler's method on Mathematica. You can do it in fancier ways that allow you to go further, but I think this is the simplest approach for now. I'd like to end this session by showing you something kind of cool. There are lots of uses for recursive equations. What I'd like to do here is show you another cool thing that happens sometimes with recursive equations. I'm actually going to make my function f here just a function of y alone. I'm going to make it 4 times y times 1 minus y. I'm not really going to worry about the t's. I'm going to update the value of y just based on plugging into the function itself. So this is definitely not Euler's method. You can, in fact, ignore all the other things except for the function. Y sub 0, I better change that to something else. I'm going to pick 0.1. And y sub k equals f of y sub k minus 1. And for my numbers, I'm going to just look at the y values. Well, I suppose I can plot k too. So this is a different kind of plot. It's not Euler's method. Different kind of situation here. I'm just wanting to show you this because it's very interesting. What's going on here? Usually when we plot functions, we see patterns. Doesn't seem to be much of a pattern here. What's going on, and why am I talking about this in a differential equations class? Well, it actually is related to differential equations. What we're seeing here essentially is an example of something called chaotic behavior. The most famous example of chaotic behavior is called the butterfly effect. And on your CD-ROM, there is an option for something called the butterfly effect. The butterfly effect is based on the idea that a butterfly flapping its wings in Mexico today might cause a tornado in Minnesota, say, 2 weeks from now. Hopefully not. But theoretically, I suppose you can't really disprove it. That's the gist of the butterfly effect. Sensitive dependence on initial conditions. Small changes in initial conditions can lead to drastic changes in long-term behavior. What you've got on the right here are a couple of boxes that you can kind of pretend contain water. And we're going to be looking at water molecules moving around the boxes, basically via convection. The red bars down here are supposed to represent a heat source, and the blue bars are supposed to represent a cool source, or a cool sink, I guess you might say. I'm going to go ahead and pick a particular starting condition in this plane here, which is actually just a slice of something called a phase space for a set of 3 differential equations that you see up at the top there. And the idea of what's going on here is that these water molecules that you see moving around were supposed to start very close together, but ever so slightly different. In fact, their only difference is in the thousandth place of the x-coordinate. They were very close together to start with, but notice that they're diverging from each other, and in the long run, the behavior is completely different. That's an example of sensitive dependence on initial conditions. This model is based on differential equations. And what this is then illustrating is that with differential equations, especially 3-dimensional ones or higher, very strange and unpredictable things can happen. It's a very, very challenging field of study. And that's the end of this video.